So we have seen how to derive the character table using the great orthogonality theorem. Now we'll go to another application of this. This is for cyclic groups, and in cyclic groups there is a relatively easier way to derive the character table, and this is what we'll see. Okay, so cyclic groups. Let's take the example of C7. And in a cyclic group, it is an abelian group. Okay, every cyclic group is abelian. That implies elements commute. Okay, so all operations of the groups, they commute with each other, and that implies that x inverse Ax is equal to A. Okay, x inverse A is same as A times x inverse. So A times x inverse x is nothing but A. So this implies each element is in its own class. Okay, so each element is in its own class. So for example, if we take C7. Okay, so C7, the elements are C7 square. So all these are not only the elements, these are also their classes. And cube, so these are the 7 elements, and they are all in their own class. Okay, so the classes are these. Okay, and since there are 7 classes, there should be 7 irreducible representations. The sum of their squares, so L1 square plus L2 square up to L7 square is equal to 7, the order of the group. So this implies L1 equal to L2 equal to L7 equal to 1. So there are 7 one-dimensional representations. So we can say gamma 1, gamma 2, gamma 3, gamma 4, oh, I missed the identity. I have to show the identity element. So there should be identity. Okay, so identity is also an element. Okay, so then you have gamma 1, gamma 2, gamma 3, gamma 4, gamma 5, gamma 6, and gamma 7. So these are the 7 one-dimensional representations, and since they are one-dimensional representations, the character of identity is 1 in each representation. Okay, now we need to fill in all these values, and we need to fill them in such a way so that any two rows treated as vectors will be orthogonal, and the sum of squares of across any row of the elements should be equal to 1. So you sum over all operations in any representation, you should get 1. So we say that sum over R. In this case, since all are one-dimensional representation, chi is same as gamma. So chi in the ith representation of R square equal to 7. Sum over all operations. Similarly, sum over all operations of chi in the ith representation times chi in the jth representation star equal to 0. Okay, so we need these two. So if you treat this row as a vector and you treat each row as a vector, then these two vectors are orthogonal to each other. So you take a dot product of this vector, that means you take a product of any two of these two elements plus these two elements and so on, add it up, you will get 0. Similarly, you take a dot product of any vector with itself, you should get 7. Okay, so these are the conditions, and we can see that that there is a simple way to satisfy all these conditions. Okay, so these are the conditions that should be satisfied. Moreover, the products should also satisfy the relation, like C7 times C7 square should give you C74. So, whatever the character here multiplied by the character of this should give you the character of this. Okay. And one easy way to satisfy them is shown right here, okay, where epsilon is equal to e to the 2 pi I divided by 7. Epsilon is chosen as exponential of 2 pi I divided by 7. So, this implies epsilon square is equal to e to the 4 pi I over 7 and so on, and epsilon raised to 7 is equal to e to the 2 pi I equal to 1. Okay. So, epsilon denotes one of the 7th roots of identity. Okay. And what you notice here is that if you define epsilon in this way, then I can choose my elements this way. I choose C7 as epsilon, then C7 square is C7 times itself. So, it should be epsilon square, epsilon cube, epsilon 4, epsilon 5, epsilon 6. Okay. And you notice that epsilon raised to 7 is 1. So, C7 raised to 7 is nothing but the identity. So, that is also satisfied. Similarly, I can take C7 as epsilon square and go ahead, then this will become epsilon 4, 6, 8, 10, 12. If I take it as cube, then it should be 3, 6, 9, 12, 15, 18 and so on. Okay. Now, since epsilon raised to 7 equal to 1, epsilon raised to 8 is equal to epsilon. Okay. So, epsilon raised to 8 is epsilon raised to 7 times epsilon. So, that is just epsilon. Okay. So, wherever you see epsilon 8, you replace it by epsilon. Epsilon raised to 10 is nothing but epsilon cube, because epsilon raised to 7 plus 3. So, it is epsilon cube. Epsilon 12 is epsilon 5 and so on, and you can go ahead and take all these elements and you can replace them, replace all these higher numbers by epsilon 8 by epsilon, epsilon 10 by epsilon cube, epsilon 12 by epsilon 5. Okay. Furthermore, you can do that. You can go ahead and do that. So, if you take epsilon raised to 24, okay, 24 is 21 plus 3. So, epsilon raised to 21. Epsilon raised to 21 is epsilon 7 cube. Okay. So, epsilon 7 cube is nothing but identity. So, it is just epsilon raised to 3. Okay. So, you can do this. You can do this for all the elements. Epsilon raised to 24 is equal to epsilon raised to 21 times epsilon raised to 3 is equal to epsilon raised to 7 cube times epsilon cube is equal to 1 times epsilon cube. Okay. So, you can express all the numbers in terms of epsilon powers which are less than or equal to 7, less than or equal to 6. Okay. Further, you can do one more manipulation, okay, which you can see this epsilon raised to 6 is equal to e to the 6 pi I or 6 into 2 pi I by 7 is equal to e to the minus 2 pi I by 7 is equal to epsilon star. Okay. So, you can easily see this, because this is 12 pi I by 7, that is 14 pi I by 7 minus 2 pi I by 7. Okay. So, that is e to the minus 2 pi I by 7. So, you notice that epsilon is epsilon star. Similarly, epsilon phi is equal to epsilon 2 star and epsilon 4 is equal to epsilon 3 star. Okay. So, star refers to the complex conjugate. Okay. So, then you can write this as epsilon square epsilon 4. Epsilon 4 is epsilon 3 star. Okay. Epsilon 4 is nothing but epsilon 3 star. Epsilon 6 is nothing but epsilon star. Epsilon 8 is epsilon raised to 1. Epsilon 8 using this relation, it is epsilon raised to 1, epsilon raised to, so, and epsilon 4 is epsilon 3 star. Okay. Now, you notice in this representation that the 7th representation is 1 epsilon 7 which is 1, epsilon 14 which is also 1, epsilon 21 which is also 1, epsilon 28 which is also 1, and so on. Okay. So, then what is done is you write this element on top. This is just the totally symmetric representation, which is always one of the possible representations of any for any group. So, you always have the totally symmetric irreducible representation. Okay. Then you write these two, gamma 1 and gamma 6. So, gamma 1 has 1 epsilon square. Now, notice this is 1 epsilon raised to 6. Epsilon raised to 6 is nothing but epsilon star. Epsilon raised to 12 is epsilon 5 which is epsilon 2 star. Epsilon raised to 18 is epsilon raised to 4 which is epsilon 3 star. So, I write it in this form. So, I have 1 epsilon square epsilon 3, okay, then epsilon 4 is epsilon 3 star, epsilon 5 is epsilon 2 star, and epsilon 6 is epsilon star. So, I write it just in terms of epsilon, epsilon square, epsilon cube, and their complex conjugates. Okay. So, then I can show that I order the table in this way. So, I collect gamma 1 and gamma 6, I collect gamma 2 and gamma 5, I collect gamma 3 and gamma 4. Okay. So, gamma 1, gamma 6, gamma 2, gamma 5, gamma 3, gamma 4. So, I write it in this form, and now what you notice is something very interesting. If you look at this row and this row, okay, this row is just a complex conjugate of this row above. So, you have epsilon, epsilon square, epsilon cube, epsilon star, epsilon 2 star, epsilon 3 star, epsilon 3 star, epsilon 2 star, epsilon star, epsilon 3, epsilon 2, epsilon. Okay. So, this row is nothing but a complex conjugate of this row. Similarly, this row is a complex conjugate of this row, and this row is a complex conjugate of this row. Okay. So, basically what we notice is that these two one dimensional representations, okay, these are two one dimensional representation, it makes sense to combine them into a two dimensional representation. Okay. This is a two dimensional representation, the two components are nothing but complex conjugates of each other. Okay. This is also thought of as a two dimensional representation. Okay. So, in some books you will find this group represent the character table represented in this format. Okay. In some other books what is done is these two are added together. So, if you add these two together you will get 2, if you add these two together you get epsilon plus epsilon star. So, epsilon plus epsilon star is equal to 2 cos 2 pi by 7. Okay. Epsilon is e to the 2 pi I by 7, epsilon star is e to the minus 2 pi I by 7. So, if you add them up you will get twice cos of 2 pi by 7. So, you can fill up this row in this form. So, you have 2 cos 2 pi by 7, 2 cos 4 pi by 7, 2 cos 6 pi by 7, epsilon 3 star plus epsilon 3 is same as this. So, 2 cos 6 pi by 7, 2 cos 4 pi by 7 and 2 cos 2 pi by 7, and similarly you can fill in for E2 and E3. Okay. So, there are two alternate ways in which character tables of cyclic groups are represented, and you find both of these used. Okay. You can show that this satisfies all the transformation properties that this other representation also satisfied. So, both these representations are used, but you should be a little careful when you use either of them. Okay. So, so that's about what I want to say about character tables for cyclic groups. Okay. Next, we have looked at parts of the character table, but we want to now look at the character table in its entirety with all the various parts of the character tables. Okay. So, let us look at a group D3. Okay. Now, D3 has three different has 3 classes. Okay. The identity element which is in one class. Okay. Then there are two C3. Okay. There is C3 and C3 square, and then there are 3 C2. Okay. So, there are 3 C2 operations, they belong to one class. Okay. Now, D3, so you can say that number of classes is 3. So, since so you have number of irreducible representations is 3. So, L1 square plus L2 square plus L3 square equal to 6. This implies L1 equal to L2 equal to 1, L3 equal to 2. Okay. So, you have two one dimensional representations and one two dimensional representations. So, I can call it A1, A2 and E. Okay. So, these are the two one dimensional representations, this is a two dimensional representation. Okay. Now, the character of identity will be 1, 1 and 2. There will always be a totally symmetric representation. Now, you have to work out what are the remaining characters. Okay. So, to work that out you use the great orthogonality theorem. So, if I call this as, suppose I call this chi of C3 in representation A2. Okay. Chi of C3 in A2. Okay. Now, it should satisfy two properties. First is that if you take the dot product of one row with itself, you should get 6. So, then this will be 1 plus chi A2 chi A2 of C3 square, and there will be 2 of these. So, into 2 plus chi A2 in A2 of C2 into chi in A2 of C2 star, and this should be multiplied by 3. So, this sum should add up to 6. Okay. This sum should add up to 6. Moreover, it should be orthogonal to this row. Okay. So, I will just denote this by alpha, okay, and this by beta. Okay. So, then you will say 1 plus 2 alpha square plus 3 beta square equal to 6. Similarly, it should be orthogonal to this. So, I take dot product of these two. Okay. So, this will be 1 plus, now I will get alpha into 1. So, and this will be multiplied by factor of 2. So, 2 alpha plus 3 beta equal to 0. So, you have these two equations, and you can solve this for alpha and beta. So, you have alpha and beta are the unknowns. Okay. So, let us work it out. So, one solution, if you just try to solve these, what you will get from the second one is that alpha is equal to minus 1 minus 3 beta by 2. Okay. And if you substitute this in the first equation, what you will get is 1 plus 2 into 1 plus 9 beta square plus 6 beta divided by 4 plus 3 beta square equal to 6. Okay. And if you now if you rewrite this, what you will find is the following. So, what I will do is multiply this by 2. So, I get 9 plus 6 15 beta square. Okay. So, the beta square term will be 9 plus 3 times 2 6 15 beta square, and then you have 6 beta plus 6 beta minus 9 equal to 0. So, you have 1, okay, 1 plus 2 is 3, and here you have minus 12, you have 12. So, 3 minus 12 is minus 9. Okay. So, you will get this equation, and if you solve this, you will get beta is equal to minus 1 or beta equal to 12 by 15. Okay. So, if you solve this, you will get these possibilities for beta. Okay. So, if beta is minus 1, let us take the case where beta is minus 1. So, if beta is minus 1, then clearly by using this equation alpha has to be equal to plus 1. So, two solutions are beta equal to minus 1, alpha equal to 1, or 12 by 15 is 4 by 5. Okay, so, if beta is 4 by 5, what should alpha be? So, if beta is 4 by 5, then 3 into 4 is 12 by 5, 17 by 5. So, minus 17 by 10. Sorry, beta is 4 by 5. Okay. So, you can check again 4 plus 3, 4 into 3 is 12, 12 plus 5 17, and this is minus 17 by 10. Okay. So, these are the possibilities. So, these two choices will be first of all they will be normalized. So, if you sum the squares you will get 1. Okay. Secondly, they will be orthogonal to this. Okay. So, if you sum the squares you will get 6. Okay. Secondly, if you take the dot product to this you will get 0. Okay. So, these are the two possible choices. Okay. Now, the question is how do you know which one to put here? How do you know which one to put here? And the answer to that is that you have to have the second set. You have to have the second set. Okay. You have to work out the two dimensional representation. So, for two dimensional representation, what you will say is that the first is the sum of squares. Sum of squares here should be 4 plus 2 chi e of C3 square plus 3 chi e of C2 square equal to 6. Okay, so this I can write as if I call this alpha prime and this as beta prime. So, I can write this as 2 alpha prime square plus 3 beta prime square is equal to, this is 4. So, that is 2. Okay. The other relation you can also write. So, this is 2 plus, so you can write 2 alpha prime plus 3 beta prime equal to minus 2. So, you can write these two relations. Okay. And this can also be solved again using the same method you can solve this. So, what you will get is equal to minus 2 minus 3 beta prime by 2. Okay. And if you substitute in here, what you will get is by 2 plus 3 beta prime square equal to 2. So, this implies, so you have a 4 and in this case you have a 4 on the right. So, that term will give me 0. So, you will get 9 beta square plus 3 beta square 12 beta prime square. Okay. Then you have 6 beta prime. Nine plus 6, 15. 15 beta prime square plus 6 beta prime equal to 0. Okay, so that will be the final result. So, this implies beta prime equal to 0 or beta prime is equal to 6 by 15. 6 by 15 is just 2 by 5. Okay. And this implies alpha prime is equal to minus 1. So, if beta prime is 0, then clearly alpha prime has to be minus 1. If beta prime is it should be minus 2/5. If beta prime is minus 2 by 5, okay, then this is minus 2 into 3 is minus 6 by 5. minus 6 by 5. So if you take that away, so 2 is, so it will give you minus 4 by 5 minus 2 by 5. So alpha prime should be minus 2 by 5. Yes. Okay. So these are the two possibilities. So if both these are equal to minus 2 by 5, then clearly this is 5 into minus 2 by 5, that is minus 2, okay, which is this side. So you can have either of these possibilities are allowed. Okay. So you had two possibilities for alpha and beta, and you have two possibilities for here. Okay. So I'll just write it here. So you can have 1 minus 1, okay, or you can have minus 17 by 10 and 4 by 5. Okay. Now this will satisfy orthogonality with this. Okay. Then you can also have, in this case you can have minus 1 0, or you can have minus 2 by 5 minus 2 by 5. Okay. So these are the two possibilities here. Now it's also important that these two should be orthogonal to each other. Okay. So these two have to be orthogonal to each other, and if you impose that condition, you can clearly see that if I take this and this, if I take these two, they will clearly not be orthogonal. If I take these two also, they are not orthogonal. Okay. So basically this second choice is not valid. Okay. So the second choice is not valid, so you can directly eliminate this choice, and also you will see that you can eliminate this choice because this is not orthogonal to this. Okay. So these two are not orthogonal to each other. Okay. So this choice can also be eliminated, and so you are left with only one choice, that is 1 minus 1 and 2 minus 1 0. Okay. So this is important. It has to be, these two rows also have to be orthogonal, and this is the only choice that satisfies that these two rows are also orthogonal, and these two are orthogonal, and these two are orthogonal. Okay. So this is the basic only possible choice for your characters. Okay. Now if you look at a character table, there are two more parts of the character table. So there are some things, there are these two parts of the character table. So there are two additional parts of the character table. Okay. And what appears here is the following. In this part, what appears is one of the following, either x y z, rx, ry, rz. Okay. So one of these, one or more of these will appear. Okay. For the group, I will illustrate this with an example. So for this group D3, what will appear here is z and rz. Okay. And here what will appear is x y, rx, ry. Okay. So what appears for D3 is z and rz here, x y in one bracket and rx ry in the other bracket. Okay. So what does this signify? Okay. So what this signifies is the following. So when you imagine that you have x, y and z axis. Okay. So you have x, y and z axis. Now when you operate by E, by C3 and by C2 on the z axis. Okay. When you operate by E, C3 and C2 on the z axis, C3 will not do anything to the z axis because C3 axis coincides with the z axis. Okay. The C2s, however, will change z to minus z. Okay. So E will not do anything, C3 will not do anything, C2 will change z to minus z. Okay. So this A2, this irreducible representation is exactly how z transforms. okay, how the z axis transforms under these operations is exactly how this A2 representation characters behave. Okay. So, therefore, z is put here. Similarly, rotation about z axis will also not be affected by C3, and C2 will change the rotation to minus of that rotation. So, these characters are like the characters of this of z or Rz. Okay. So, z and Rz behave exactly like A2. Okay. So, in other words, these various representations, they are like different ways to express the various operations, and this way of expressing operations is consistent with z and Rz. Okay. Now, let us take the two dimensional representation. Okay. So, the two dimensional representation E, now what this does, your identity is not nothing happens to identity. Now, what you notice is that C3 the character is -1 and C2 the character is 0. Okay. You can think of it this way. So, x and y, what happens to x and y under C3? So, when you operate by C3, x and y get mixed into each other. Okay. So, C3 mixes x and y. So, C3 does not change z, but it mixes x and y. Okay. And C2 will not do anything to x and y, okay, but it will change z to minus z. Okay. Depending on which way C2 is oriented, it might also affect x and y, but in general it changes z to minus z. Okay. So, the point is if you work out the character of if you work out the matrix of transformation for x and y, okay, and you work out for Rx and Ry, okay, what you will find is that their characters are exactly represented by this 2 -1 0. Okay. So, and what this represents is that x and y get mixed, Rx and Ry get mixed, okay, but together in this is the two dimensional representation which transforms exactly like these characters. Okay. It is not hard to see. So, we will illustrate that right here. So, you can think of it this way. So, suppose I take x y. Okay. So, suppose I take x y and I imagine that I have a two dimensional vector x y with components x and y, and I operate it by C3. C3 is about the z axis. Okay. Then the new vector will be x prime y prime, okay, and this can be written as cos 2 pi by 3 sin 2 pi by 3 minus sin 2 pi by 3 and cos 2 pi by 3 times x y. Okay. So, the transformation from x y to x prime y prime under rotation under C3 is this matrix. Okay. So, C3, the matrix corresponding to C3 is this. Okay. Now, what is the trace of this matrix? The trace of this matrix is -1. The matrix corresponding to 0 to the identity is just that has trace 2. Now, the matrix corresponding to C2. Okay. So, let us take so this has 3 C2 axes which are perpendicular to the z axis. So, if you take one of them along the x axis, okay, then the matrix of transformation will be shown as this, okay, because the x coordinate is not changed, y coordinate changes to minus y, z of course changes to minus z, but we are not showing z, we are just showing x y. Okay. So, the trace of this is 0. Okay. So, what this means is that if you think of a vector like x y, a two dimensional vector x y, that will transform exactly like this representation. Okay. So, this representation is how a vector a two dimensional vector x y transform. Similarly, r x r y, these rotations will also transform according to these with just these characters. Okay. So, this is the third part of the character table, which is where only these 6 elements will appear, and each of them will tell us how these operations transform under these symmetry operations. Okay. There is a fourth part of the character table. Okay. So, here we only used x, y, z, r x, r y, r z. Okay. Now, sometimes there are various products of like x into y or x square plus y square, okay, which transform exactly according to certain representations. Okay. So, for example, in this case it will be x square plus y square and z square. Okay. So, if you take z square, okay, z square, if you operate C3 on z square, the trace will be identity, C2 on z square, the trace, I mean you can easily show that C2 takes z to minus z. Okay. So, z square nothing will happen to z square. Similarly, C2 will preserve x square plus y square, okay, and C3 will also preserve x square plus y square. So, these are preserved, and so they transform like A1. Okay. So, this product appears in the first row. Okay. Now, what are the products that transform like A2? In this case, actually there is no simple product that transforms as A2, but there are some products that transform as E, and that is x square minus y square x y. Okay. So, it has to be a two dimensional representation. Okay. Or you can have x z y z. Okay. So, if you had a vector like x square minus y square and x y, so which had two components x square minus y square and x y, you could have done exactly, you could have seen what is the effect of identity, and that will have a character of that will have character 2. What is the effect of C3, okay, on x square minus y square and x y, okay, and you can show that will have character -1. Similarly, if you take C2 will you can easily show C2 will take x to will preserve x and change y to minus y. Okay. So, then x square minus y square will be preserved. Okay. So, and then x y will change sign. So, you have 1 minus 1. So, you will get 0. Okay. So, you take a vector of the form x square minus y square and x y, okay, and you operate it with C2. Okay. So, then what you will get is the following. So, C2 will take x to C2 will keep x as it is. So, you will get x square, C2 will change the sign of y to minus y. So, x square minus y square will remain x square minus y square, x y will become minus x y. Okay. So, then you can write C2 is equal to 1 0 0 minus 1. Okay. So, 1 0 0 minus 1. So, these operations. So, this vector transforms like E. Okay. Similarly, you can show that x z y z, a vector with components x z and y z will transform exactly like this. Okay. So, these products are represented, these simple products of various coordinate axes are what is represented in this fourth part of the character table. Now, these are actually extremely important. You will notice immediately that that these products seem very familiar. Okay. So, this looks like you immediately identify, you have seen the dxy, dyz, dxz, dx square, y square. Okay. So, you immediately see that that there are a lot of similarities, and in fact one of the major applications of group theory is to find out which orbitals mix with each other, which orbitals overlap. Okay. And so, when we look at an application of group theory in quantum mechanics, all these, it is important to know which representations allow various products to mix. Okay. So, this concludes the character table, and I urge all of you to go back and you know, try to look in any book, look at a character table of any group and try to identify, try to derive it step by step. And when I say derive all parts, not just this part, not just the characters, but also these parts. Okay. And when you get if you have done it for one or two groups, then it is fairly straightforward to do it for all the other groups. Okay. Now, before I end the discussion on character tables, I want to mention one other theorem, that is one other relation that is extremely useful in for a lot of practical applications. So, now this has to do with reducible representations. Okay. So, now if a representation is reducible, okay, then the matrix corresponding to that representation, okay, so the matrix corresponding to that representation, if it is reducible, it factors into various it will factor into various other matrices, and then you will have 0 everywhere else. So, all these will be zeros, and it will factor into, this might be a 3-dimensional, this might be a 1-dimensional, and so on. So, any reducible representation can be factored into irreducible representations. So, this is all these are irreducible representations. Okay. Now, if you do any if you do this, then sometimes the same irreducible representation might appear multiple times. Okay. So, when you take any reducible representation, you write it in terms of irreducible representations, then sometimes for certain matrices you can easily imagine that one irreducible representation appears multiple times. For example, if you had the D3 group, D3 group had 3 irreducible representations. They were A1, A2 and E. E was a 2-dimensional representation. Now, if you had you could imagine that you have a matrix that is reducible. Okay. So, you have a reducible representation, and in this when you block diagonalize it, you have A1 appearing once, E, A1, A2. So, you could imagine that something like this. So, then what you would say is that, and let me show it like a square matrix, and once again you have A2. So, you say that A2 appears twice, A1 appears twice, and E appears once. Okay. Now, the question is, if a reducible representation also has, even in a reducible representation you can speak of characters. Okay. So, I can ask gamma for a reducible representation. Okay. I can ask what is the character of some operation R Mn. I can ask some question like that. Okay. So, for a reducible representation, what is the character of R Mn? Okay. How is this related to the characters of the corresponding irreducible representation? Okay. So, I can ask the Mn character, or I can ask what is the character, the trace of the reducible representation of R. So, in the reducible representation, what is the character of a particular operation? Okay, so, this is one matrix element, this is one matrix element. So, this is the mth matrix element. This is the character or the trace of the. So, this is a trace of the matrix corresponding to the reducible representation of operation R. Okay. So, how is this related? So, how is this related to the trace of the irreducible representations? Okay. Now, now you can immediately look at this and you can say the answer. So, chi in the reducible representation of R, that has to be. So, if you had something like this, what you notice is that E appears once. So, the trace of this should be trace of A1 plus trace of E plus trace of A1 plus trace of A2 plus trace of A2. Okay, trace of this matrix is trace of A1 plus trace of E plus trace of A1 plus trace of A2 plus trace of A2. So, you can generalize this in the following form: sum over all irreducible representations. Okay. So, sum over all irreducible representation A I chi I of R. So, this is the character of R in ith irreducible representation, and this is the A I is the number of times irreducible representation I appears in reducible representation. So, how many times does the irreducible AI? Okay. And here you can use the great orthogonality theorem. So, you can immediately use the great orthogonality theorem and you can say that AI is equal to sum over all R. Okay. So, it will be chi I of R and chi reducible of R. Okay. So, and this divided by H I 1 over H, sorry. Where H is the dimension of ith irreducible representation. Okay. So, you can show this relation easily. You can just use the great orthogonality theorem. If you multiply both sides by chi I of R, then you can show this. You can show such a relation. Okay. So, this is a very this is an extremely useful relation. It looks very much like the usual when you expand one vector as linear combinations of basis vectors, then the coefficients of the basis are got by dot product of this vector with the basis vector, and it looks exactly like that, and in fact that analogy is useful and correct. Okay. Only thing, the great orthogonality theorem always has an H factor that appears, and so this relation is very useful in application. So, again, when you are doing when you are constructing linear combination of orbitals in various theories, okay, then such relations will prove to be extremely useful. Okay. So, with this we will close the discussion on the character tables and characters. Next we will go to something called symmetry adapted linear combinations, and this will be this is where we get into the heart of applications of group theory.